All right, so we're going to go over today models of the atom, history of the atom, so a little bit of kind of the history of chemistry, really, okay, and just kind of some basic stuff about atomic structure, right? Anytime you have a lesson where I'm going to be actively teaching you something, okay, it'll get set up like this. It'll have the lesson number and some key points set up the same way in your notes package, okay? Those key points are the things that I would definitely have a look over, as they would be things I would end up on a test or a quiz or something like that. Okay, so the big things here, we want to look at how the theories of the structure of the atom were developed, okay, and look at the parts of the atom and their characteristics, so atomic structure. Okay, so chemistry hasn't always looked the way it looks now. Okay, there were these group of people way back that were called alchemists that did a lot of the kind of introductory work. We'll talk about them before that, or in a minute here. But even before that, in many ways in human history, we've used science before we really understood how it worked. We just know that it did work, so we used it. Okay, and we used chemistry for lots of things. We used it to like tan leather, dye cloth, prepare or store foods. Okay. And that was because during those times, those were things that were necessary for survival. You didn't necessarily have the time to study why does this work. Didn't matter why, it just did. Okay? The why comes when you have time to study things, and that didn't come until much later. Okay? But obviously we were using physical and chemical properties, just chemistry, okay, of materials to do certain jobs for us. Okay? Now, the earliest idea of the atom was actually first rejected. Okay? It was thought up by a Greek thinker, which is like the best job you could have in ancient Greece. Okay? To be a thinker in ancient Greece was like the creme de la creme of jobs. Okay? You just sat in the Acropolis, and people like waved palm fronds to keep you cool and fed you grapes all day, and basically just had to come up with cool ideas. Okay? It was a sweet day. Okay? One of those, people like Plato and Aristotle, they were thinkers. Okay? Democritus was also a Greek thinker. Okay? And he proposed that all matter was made of these things called atomos, okay? Which were indivisible particles. Right? Now, we know actually his idea is correct, but at the time his idea was not very popular because he couldn't prove it. It's a nice idea, but he had no way to prove that everything was made of these tiny little particles you couldn't see. Okay? The other reason his idea was not really well accepted was because they already had an idea in place that worked very well for the structure of matter. They believed all matter was made of how many elements? 4. Earth, air, water, and fire. Okay? This was a really solid basis, okay, for the understanding of matter for the Greeks. Okay? They would, they would be able to explain how certain things work. Like, for example, if a volcano erupted and lava was flowing, okay, they knew that lava came out of the earth, so it was some parts earth. It was really hot, so it was some parts fire. But it would flow, so it was also some parts water, which really isn't all that far off. Okay, and it made good sense. It was easily explainable. Okay, steam. Okay, to make steam, you had to heat water. So steam must be some parts air, some parts water, and some parts fire. Okay, these were the things you had to mix together to get something. Right? They had like almost like a periodic table of sorts that helped to explain how much earth, air, and fire, and water was in everything. Okay, and so it was a well-accepted idea. So Democritus' idea of these tiny invisible particles kind of went by the wayside. People were like, nah, the other idea works better. Why don't you think up something else? Okay, it wasn't all bad for Democritus. He did think up something else. Sounds like his name. Democracy. So it wasn't all bad. Okay, he just went more into the arts than the sciences, okay, to find his success. All right, but 2,000 years later, okay, we now know that, hey, that idea was actually true. Okay, during the Middle Ages, a lot of experiments were run that taught us a lot about the behavior of matter. The problem is that they were performed by people known as alchemists. Alchemists were not like true scientists. Okay? They were in it for the money. They would have these like secretive little labs, like you're a good picture like a wizard being in, like, dark and cold, and they'd have all these like potions boiling and stuff like that. That would be like what an alchemist's lab would look like. Okay? And they were trying to do things in order to get rich. They were trying to manipulate matter and turn it into other things. Okay? We now know that most of what they were trying to do is impossible. But they didn't know that because they didn't have the understanding of matter that we have. Okay, so one of the big things alchemists were trying to do was to turn cheap substances into gold. So, like, take a pile of lead and turn it into gold. Right? Now, we know that's impossible. Okay, we now know that. Okay, but they didn't know that. Okay, and the reason they didn't understand that it would be impossible to turn one thing into something else is because they were able to turn things into other things. They were able to have chemical reactions happen and see things in front of them change from one form to another. Okay? But what they didn't understand was the difference between like a pure substance, and a compound, and an element, and a mixture. They didn't understand those kind of things like we do. So they didn't realize that to turn lead into gold would require a fundamental change in every single particle that the lead was made up of. Okay? Not something that we can do. Right? But to mix together, let's say, tin and copper and get brass, that was possible. That looked like turning metals into gold. Brass looks like it's not. Okay? But it looks like. Right? It's a totally different process, though, than actually turning something into real gold. You kind of follow me there? Right? So that's what the alchemists were trying to do. They were also trying to come up with like things like potions that would make people live forever. Okay? Like the elixir of life and stuff like that. A lot of people died experimenting on that. It's like, oh, I'm going to drink this boiling yellow goo, and I'll live forever. Except it's like drinking a spoonful of Drano. Okay? Yeah, it's not good for me. Okay? It'll clean you out, but it'll leave you hollow inside. All right, so those are all the kind of things that they did. But they did discover a lot of different behaviors of matter, and as a result, okay, we learned a fair amount about that. Okay, but it wasn't until these two guys came along that alchemy turned into a real science. Okay, and these two guys are Roger Bacon and Antoine Lavoisier. They are credited with coming up with the scientific method. So the scientific method involves what you would do in a lab, right? You have a problem that you investigate. You have variables, manipulated, responding, controlled variables. You have a hypothesis that investigates your problem, a procedure you follow, results that you get, analysis that you make, a conclusion you draw, okay, and then you're done. Okay? That's the scientific method. Okay? The biggest part of the scientific method is communicating what you discover. That's what the alchemists didn't do. Okay? They would do a lot of trial and error stuff and just record whether it worked or not and not share that with anybody. Okay? But turning it into a real science like chemistry involved a lot of the sharing and discussion and repetition of experiments. Okay, so if I take a small piece of any material, like let's say I have like a cube that's made out of lead, okay? If I keep cutting that cube smaller and smaller and smaller, okay? If I could cut it down to the point where I would have a single atom of lead. Now, nobody has a knife that thin, obviously, okay? But if I could, eventually I would get to the point where I couldn't cut it any further, okay? That single part of it is one atom of lead, and it has all the same properties that the big chunk had, because the big chunk was just made up of more. Okay? So even a single atom still retains all the same properties as a much bigger sample of the same material. Okay, they have all the same physical properties, chemical properties, melting point, boiling point, all that kind of stuff. Okay, so the atom is the smallest particle of an element that still retains the properties of that element. Okay, so that's something we should definitely know. Okay, an atom is the smallest particle of any element that still retains the properties of that element. If I split that, okay, it's no longer that material anymore. Okay. Now, can I actually split an atom? Yes, I can. I don't have the materials or the tools. We can. Okay, as a race, yes, we can. We know how to split the atom. Okay, but thankfully, I can't split the atom while I'm chopping carrots. Okay, at home. Right? Atoms are obviously way too small. Okay? The sharp edge of a knife is still hundreds of thousands, if not millions, of atoms thick. Okay? It would be like trying to cut a carrot with a skyscraper. Okay? You're just not going to do it. All right? So, yeah, I can't split the atom by a physical means like that. Okay? But I can split it if I have the right technology present. When I do split it, I actually change the atom. Now I have different particles. Okay? They no longer have the same properties the atom had before. Okay? I might be looking at protons, neutrons, and electrons. Okay? The parts of them. Okay? So, protons and neutrons, okay, we know now that they reside in this place in the middle called the nucleus, okay? The electrons reside in what we call the electron cloud, okay, which is a region of charged particles that surrounds the nucleus. Okay, questions on that one? Don't be afraid to ask as I go here, guys. All right, so it wasn't until the late 1700s, okay, that chemists were able to relate all the chemical changes to events that happen at the level of individual atoms. Okay, again, this is what the alchemists didn't understand. They didn't realize that when they put two things together and saw something new get formed, that it was still made up of all the stuff they started with. They hadn't actually created anything new. Okay, it would be like if I took sodium metal and combined it with chlorine gas. Okay, this is a silvery gray metal. This is a green gas. But if I was to combine them, I get this. It's just table salt. Okay, if an alchemist did that, he would think, I created something new. And while he's partially right, sodium chloride is a new substance, he hasn't made any new elements. His new substance is just a combination of what he had before. Okay? That's what the alchemists didn't understand, was that they weren't really making anything new. They were combining them in different ways, but they weren't making anything new. Okay? That sort of makes sense? So that's what chemistry determined that alchemy never did. Okay, so John Dalton was the first person to come up with and kind of resurrect this idea of the atom. Okay? We call it the atomic theory now. And it had 4 points. Okay? The first point he owes to Democritus. Okay? The first point of the atomic theory is that all matter is composed of tiny, indivisible particles called atoms. Okay? Now, indivisible means what can't you do to them? Divide them. Okay? Now, we know that we can divide atoms now. Okay? But can I just do that on my own? Not really. So he's still essentially right. If I divide an atom, it ceases to be an atom of what I have. It becomes something else. Okay? His second point was that atoms of the same element are identical. Atoms of one element are different from those of any other element. So if you look at that periodic table I gave you there just a few minutes ago, okay, we can see that if we're looking at, let's say, nitrogen and oxygen, okay, they're both gases, but nitrogen, okay, has 7 protons, where oxygen has 8 protons. Okay, that's what makes them different. Okay, the number of protons in the nucleus of any atom is what makes an element different from another. Okay, if I have a whole tank full of oxygen, every one of the atoms in there is the same. That's 99% true. Okay. Not every oxygen atom is exactly the same. Okay? There's these things called isotopes. You've never heard of that term before. Okay. An isotope is an alternate form of an atom. Still has the same number of protons. Every oxygen atom has 8 protons. That doesn't change. But there are occasionally oxygen atoms that have more or less neutrons than normal oxygen atoms have. Normal oxygen atoms have 8 protons and 8 neutrons. But there are some forms of oxygen that may have 9 neutrons, or 7. Okay? Which makes them slightly different. But for all intents and purposes, they're all different. Okay? Alright. Third point of the atomic theory has to do with the formation of compounds. Okay? This thing that we talked about right up here. Okay? atoms of different elements can combine with one another in simple whole number ratios, and that's important. Simple whole number ratios to form compounds. Okay, that means that when a reaction happens and a compound is formed, I only ever have whole atoms in that compound. Okay? I don't have like half an atom or something. Okay? So if we're looking at how we write the formulas for chemical compounds, okay, like let's say I had this stuff. Okay? There's how many sodium atoms there? 2. How many oxygen atoms there? 1. Okay? I wouldn't write it like this. Because now I'm saying there's 1 sodium atom and half an oxygen atom. We just said that atoms are indivisible. I can't have half an oxygen atom. That's not oxygen. It's beryllium. Okay? Something else. Right? I can't have half of something. So you never see something written like that. That's what Dalton's third point is talking about. Okay? When atoms combine, they always combine in whole numbers. Okay? They don't split apart, okay, and do something strange. Okay? Point number 4 was the death of alchemy. Okay? Alchemy was trying to turn lead into gold. Okay? Turn one element into another element. We know that's not true, okay? Because his 4th point tells us what can happen in a chemical reaction. In a chemical reaction, atoms can be separated, joined, or rearranged. Atoms of one element are not changed into atoms of another element. Okay? So in a chemical reaction, I have the same elements on both sides of the reaction. If I start with sodium and chlorine, I'm going to have sodium and chlorine on the other side. Okay? They might join, they might separate, they might rearrange, but I can only have sodium and chlorine. I'm not going to magically produce titanium from them. Okay? So what we've seen here, what I wrote down for you before, was an example of a reaction where atoms join. Okay, sodium and chlorine combine to form sodium chloride. Okay, a balanced reaction looks like that. Okay, a reaction where atoms would separate would look like this. Okay, water separates into hydrogen and oxygen. Okay. Have I changed any of the elements in either one of these reactions? Okay, on either side of the arrow, I still have the same elements. It can get more complex than that. Okay, it could be like if I was using my barbecue. Okay, I'm burning propane. Okay, to burn something with gas, you need oxygen. Whenever you burn something, your products are carbon dioxide and water. Did I create any new elements? Nope. I have carbon over here, I have carbon over here. I have hydrogen over here, I have hydrogen over here. I have oxygen over here, I have oxygen over there. Okay? I didn't create any new elements. I rearranged them for sure. Okay? But I didn't create anything new. Okay? Can even go as far as something like this. Okay. Double replacement reaction between sodium iodide and lead 2 chloride. Okay. And on the other side, do I still have sodium, iodine, lead, and chlorine? I didn't create anything new. Okay. That's what Dalton's atomic theory says happens in a chemical reaction. Okay. Would those 4 points be something you should know? Yes. Yes. Like I would definitely ask you about them on a quiz test. You might want to highlight them somehow. write them down or something because they're definitely both. Okay, so Dalton comes up with this atomic theory. Works really well to explain how chemical reactions occur, okay, why matter behaves in certain ways. Does a great job of explaining all that. What it doesn't say is the question that was immediately on everybody's lips. Okay, fine. What does it look like? What does an atom look like? And Dalton's answer was, I don't know, they're really small. I can't see them. And they're like, yeah, like the story, what do they look like? Okay, so he had to come up with something. And the most natural thing to assume an atom at that time looked like was a sphere. Because, well, the sun was a sphere, the moon was a sphere, the earth was a sphere. By the way, the earth is round. Okay. If you're one of those crazy flat earth people, earth is round. Okay, anyway, so he just assumed that, naturally speaking, spheres must be kind of a natural shape that just occurs. So atoms are just a ball. Okay? And there really wasn't any evidence against that at Dalton's time. We didn't know about protons, we didn't know about neutrons, we didn't know about electrons. They didn't know any of that stuff. So it was safe to assume that, yeah, they were really, really tiny little balls. Okay? And we couldn't see them. That worked. It still explained how they could rearrange, how they could join, all that kind of stuff. There was nothing really wrong with that idea. Okay? Nothing wrong with it until somebody performs an experiment that can't be explained by atoms being a little ball. Okay? That experiment, okay, was performed by a person named J.J. Thompson. So sorry, this is Dalton's solid sphere model. Okay, that was the first model of the atom. The atom is a ball. Okay. Now, J.J. Thompson was doing experiments in what we call electrochemistry. Okay? He was producing electric currents by chemical reaction. Dalton's solid sphere model couldn't explain where he was getting the flowing charges from. Okay? Because a solid sphere can't travel through a wire. Okay? I can't take this ball and force it to travel through a copper wire and transfer a charge from one place to another. Okay? So his model of the solid sphere didn't explain where these electrical charges were coming from. So J.J. Thompson said, I've discovered a new particle. And this particle is part of the atom, but it's only loosely embedded on the surface of it. And when chemical reactions occur, the atoms get shaken really badly, and some of these things fall off, and they're charged. And when they fall off, they can flow, and that's electric current. Since it's electric current, I'm going to call these particles electrons. Okay, so that's where the idea of the electron came from. J.J. Thompson discovered the existence of these charged particles, okay, called electrons that can come off of an atom, and they can, okay, and flow from one thing to another. Okay, so what he did is he modified the solid sphere model to become what he called the plum pudding model, because I guess it looks like pudding with plums in it. Okay, but he said that the electrons were embedded on the surface of the solid sphere and that they could come off. Okay, that didn't change the material, but it could change the material's charge. Okay, and that explained his experiments. It explained his results, but didn't, throw sand in Dalton's face too badly. Okay, so everything was kind of cool for those two ideas. So the solid sphere model was out because it couldn't explain these flowing charges, and the plum pudding model was in. That's when things get crazy. Because right after electrons are discovered, we start discovering all kinds of other particles that are part of the atom. They can't be explained by this model either. So we go through this whole mess of failed models that we won't even discuss, okay, that talk about what this is part of an atom. An atom looks like this, and it looks like this, and they were all wrong. Okay, but as things went along, we discovered more and more of these atoms. Okay, like Chadwick discovered the proton, and so on. Okay, so protons were discovered, okay, and that was due to the fact that chemists agreed atoms had to be electrically neutral. If they had these negative charges on them, then there had to be positive charges that would balance them off. And then they discovered that if it was only those two particles, all matter was way too heavy to be explained by only being made of two particles. Okay, because they knew that when an electric current flowed through a wire, the wire didn't get heavier. So electrons had to be very, very small, very, very light. So they said there must be another particle in the atom that accounts for the extra mass, but it can't be charged, so it's neutral. So it's a neutron. I mean, the names of these make sense. Okay, so they came up with lots of different ideas for what the atom would look like, but none of them were really right. Okay, so yeah, Chadwick discovered protons. Okay, we're not the only. Sorry, Chadwick discovered the neutron. Sorry. Okay, neutron carries no charge in it. Okay, and things progressed from there. Okay, so we had all these different ideas of the atom. Okay, it wasn't until a guy named Ernest Rutherford came along that we got a true idea of what an atom looks like. Rutherford designed what at the time would have been like a brilliant and revolutionary experiment. Okay, to prove, he was actually trying to prove that the nucleus existed, but it was incredibly small. Okay, so what he was going to do is he was going to take a thin sheet of gold foil. Okay, so just like tinfoil, but made out of gold. Okay, and it was going to be really, really thin, so it would feel like a Kleenex almost, but made out of gold. So really, really thin. Okay, and he was going to shoot alpha particles at it. Okay, like an X-ray machine, essentially. Okay, so this X-ray machine was going to shoot particles at the gold foil. Rutherford's idea was that all of the X-rays would go right through the gold foil, okay, just like they go through your tissue. Okay, they reflect off of your bones, right? But they go through your tissue, so you can show them what your bones look like. Okay, he thought that atoms would be so small that all the alpha particles from the X-ray machine would go right through the gold foil. Okay, and so we'd have a piece of photographic film on the other side of the foil. Okay, I do. All right, so he's got this X-ray machine here. Okay, it's shooting particles at the gold foil. Okay, and what he figured was the atoms are so small, and there's so few of them because I made this foil really thin, that they'll all just go right through, and I'll get this exposed area on the film at the back. Okay, just like what would happen with you with an X-ray going through your muscles. Okay, but he thought it would just go right through like that. Okay, instead, what he discovered was he was getting spots of exposure on this film everywhere. Lots of them were behind. Okay, he did get most of the exposure to be behind the gold foil, which means most of the particles did, in fact, get through the foil. But they didn't go straight through. They would hit something and be deflected. Okay, their path would be altered. Some went straight, but some would have their path altered, some significant. Okay, so what he drew was something like this. He said, the nucleus is way bigger than I thought it was. Protons and neutrons are a lot bigger than electrons are. And they make up this dense region in the middle of the atom called the nucleus. That's what the X-rays were hitting. So the X-rays would hit a nucleus and be deflected. And so this ray here would be like this one over here. So it would go through the gold foil, but it hit an atom and was deflected over this way. Okay, lots of them got all the way through. They didn't hit any nuclei on their way through, so they went straight to the back. Okay, other ones would hit the nucleus almost straight on and bounce back. Okay, this was shocking to him because it wasn't what he predicted would happen. Okay? He said it was like shooting like an artillery shell at a sheet of paper and having it bounce back. Okay, he was so surprised at how many of the X-rays were actually deflected. Okay, giving us an idea for how big the nucleus and thus the atom really was. Okay, so because of this experiment, he proved the existence of the nucleus and the nuclear model of the atom. So Ernest Rutherford, like second most important scientist next to Dalton, if we're talking about the atomic structure and structure of the atom. Okay, he proved the existence of the nucleus, okay, which was huge, okay, with his gold foil experiment. So I would make sure you know something about the gold foil experiment and Rutherford, because he's pretty important. Okay, questions on that one? All right, so once that experiment was done, now everyone was fine with, okay, there's a nucleus. The protons and the neutrons are there. We're good with that. What do the electrons do? They're tiny. They're moving. We can't see them. Okay, what are they doing? Are they orbiting the nucleus like planets orbit the sun? Do they move all over the place? Okay, can they fly off? Can captured what's going on with them. Nobody really knew, and there really wasn't a whole lot of science out there to prove what was happening with the nucleus, or with the electrons. Okay, so there were a couple of different ideas about what was going on with the electrons. Okay, the easiest idea would be that because they're negative and the nucleus is positive, they would be attracted to the nucleus like planets are attracted to the sun and the moon is attracted to the earth, and they would naturally do what? Orbit. Yeah, move in a circle. I mean, we have evidence that that's what things do when they're attracted to each other. They move towards each other, or they orbit each other. So that made sense. Okay, and so people said, we see that there's evidence that electrons are moving. They're probably moving in circles, but they can't all be at the same distance, because if they are, what would happen to them? They'll run into each other. Okay? And we don't see any evidence that they do that, so there must be something that keeps them apart. Well, that something that keeps them apart is something that doesn't work for gravity. Right? If two planets are in the same orbit, they'll hit each other because they'll be attracted to each other. What are two electrons going to do to each other? They're going to repel, right? They're both negative. Like charges repel, and opposites attract. Okay, so that kind of held up this idea that if I took a picture of an atom, I would see electrons frozen in time and space in these positions. Okay, so people had this idea that, okay, they orbit the nucleus. But we discovered actually later that they don't, or that these orbits are not necessarily fixed. This electron doesn't always stay here. If this electron gains energy, it can become excited and jump to a higher level. Okay? It would be like the equivalent of, I make Mercury go way faster than it's going now. If I do that, it'll fly further away from the sun. Okay? And that's what electrons do. If they get sped up, they gain energy and get excited, they actually jump from one orbital to another. Okay? And get further away from the nucleus. When they start to lose that energy, they'll fall back down. Okay? This is actually what causes, or what supplies plants with the energy for photosynthesis. Okay? In the chlorophyll molecule, when chlorophyll gets hit by the sun, by sunlight, the electrons in the chlorophyll jump to further levels from the nucleus. When the sun is gone, they fall back down, and the energy they give off is what the plant uses to make sugar. Hey, Mrs. O, what's up? Okay, so like I was saying, the chlorophyll, okay, the way it works is it actually has the electrons within it will gain energy, they'll go away, and then at night, when the sun's not there to give them the energy that'll hold them there, they'll fall back down, and when they do that, they release their energy. That's what the plant uses to break carbon dioxide and water apart and make sugar. Okay? It's also what glow-in-the-dark materials will use in order to glow in the dark. Okay? So if you've got, like a watch face or something like that, that when you put it in the sun, okay, and then you go in the dark, it glows for a little while after. You guys have seen materials like that, right? Okay? That's how they work. Their electrons gain energy from the sun, and then when you go in the dark, they fall back down, and when they fall back down, they give off that energy as light. And so they glow for a short period of time. Okay? The planetary model of the atom couldn't explain electrons jumping around. Okay? It just didn't explain that. So it's sort of partially accepted, but what's currently accepted is what we call the electron cloud model. Okay? And that was developed, I guess, by Louis de Broglie. De Broglie's electron cloud model is the model we currently accept. Electrons are going to be found in a cloud surrounding the nucleus. Their locations can be not determined exactly, but they can be located with a degree of probability. Right? I would predict an electron would be in this region, and that would be likely. But I can't say for certain that it would be there. Okay, that's de Broglie. Okay, so the thing that de Broglie's model explains is basically how photosynthesis works. Okay, that electrons can jump or fall from one level to another depending on the energy of the atom. Okay, so the de Broglie model is our currently accepted model of the atom. Okay, so it's the electron cloud model. Okay, so if I was to ask you to draw a picture of an atom of lithium, how would you do it? And let's say in this picture I would want to see how many protons there are, how many neutrons there are, and how many electrons there are. How would I determine those numbers? It's okay if you don't know this.
Periodic table.
Periodic table will tell me. Okay, so if I want to draw an atom of lithium, the first thing I need to know is how many protons does it have? Okay, well I can determine the number of protons by simply looking at the atomic number. Okay, the atomic number is for lithium is 3. That's the number of protons in an atom of lithium. Right? So what I would simply do is draw 3 protons. Okay, what else is in the nucleus with the protons? Neutrons. Okay, so to determine the number of neutrons, I take the atomic mass for lithium, that's 6.94, and I subtract the number of protons, or the atomic number. Okay, because the atomic mass of any atom is basically the neutrons and the protons. Electrons are so small that they basically contribute nothing. When we're talking about the mass of the atom, they're that small. Okay, so I take the total mass of the atom, subtract how many protons it has, and that'll leave me with how many neutrons it has. Now, this is 6.94. 6.94 minus 3 is going to give me 3.94. Can I have 0.94 neutrons? How many do I probably have? 4. Yeah. Okay, so then I would put in 4 neutrons. Okay, how many electrons does lithium have? 3. Remember, an atom has to be electrically neutral. If it has 3 protons, it has to have 3 electrons. Where am I going to find those? In the cloud, right? That's all you would have to draw. If I asked you to draw a picture of an atom of lithium, I would want to see 3 protons, 4 neutrons in the nucleus, and 3 electrons in the... Okay? That shows me you know we currently accept the electron cloud model, that you know that protons and neutrons belong in the nucleus, and that you know how many of each particle there are. Okay? That'll be a 5-mark question. So, just to remind you, okay, number of protons, you might want to write this down, okay, equals the atomic number. Okay, so number of neutrons equals atomic mass minus atomic number. And the number of electrons also equals the atomic number. By the way, that's the number of electrons, not the hashtag of electrons. Okay? That symbol also means number. Okay. Tomorrow's Tuesday, but you don't have a quiz. I'm not going to do that to you in a second. But tomorrow, we are going to be using the stuff we've learned today to answer some questions about atomic structure. Okay, they're in your workbook, but that's what we'll be working on today. Don't do those for homework tonight. They're not for homework. Okay? Just that's what we're going to be working on tomorrow. Okay? And then we'll start into naming ionic compounds tomorrow as well. Okay? Make sure you keep that periodic table and formula sheet somewhere where you can always find it, because it's really important that you have it. Okay? And we will see you guys tomorrow. Okay, we've got about 3 minutes or so left here, but I'm not going to get any further than that today.